Okay. So today we have Felipe Murgas. He is a PhD student here at the ISE and arrived in 2009 after finishing his master's at the university in Chile. He is doing his PhD with Enrique and will probably finish next year. And now he's going to tell us about part of his work observing planetary transits with the GTC.
Okay. Okay, can you listen? Is the volume okay? Okay. So, well, today I'm going to talk about using GTC to observe planetary transits. This work is part of my thesis project. And I work with Enrique Payet and my PhD advisor, and a lot of people from IAC and also from outside IAC. So, a little bit of context. This is a nice plot showing the past 20 years of exoplanet. You have the number of planets of secure detections per year, and also the different methods that we are using to detect these planets. The first planetary objects comes from 1989, but usually in most of the papers that review the exoplanets, the date they put is 1982. So to me it was a surprise, because I also had that date as the first planetary mass object discovered. But the one in 1981, it's Jupiter, well, a really fat Jupiter of 10 Jupiter masses as the minimum mass. So it's probably more a brown dwarf than a planet. But the ones that first were discovered, they used the pulsar timing method. So these are planetary objects that orbit around the neutron stars, and by the delay of the time of arrival of the signal, the people could infer the presence of a planetary object around those death stars. But in 1995, the first planet orbiting a main sequence star was discovered, 51 Pegasi. So you can see that after 1995, everyone jumped in and trying to do his own search using radial velocities. And the second landmark, I guess, is in the year 2002, when the first transiting planet was discovered. So after that, again, a lot of people start searching for planets using the transit method. Of course, there are other methods like direct imaging and also microlensing. And also in the future, using Gaia, we will have astrometry to search for planets. But as you can see, the number is increasing every year. And so far, we have more than 800 planets and also 2,600 and something Kepler candidates. So this number will increase in the following years. So today I'm going to talk about transiting planets specifically. So what makes them so special? The first thing that you have to know is that to detect a transit, you need to be aligned with the line of sight with the object. So the first information that we can get for a transiting planet is the inclination with respect of the plane of the sky. So since it's transiting, we know that it's more or less 90 degrees. So when the planet passes in front of the star, it provokes a little dim of the brightness of the star, and we can measure that depth and that of that eclipse, and with that we can get the ratio of the radius between the radius of the planet and the radius of the star. So if we combine that with radial velocities, what we can get from radial velocity is the planetary mass. Of course, this is due to the knowledge that you have of the star. So you have to really have a good observation and constrain the physical parameters of the stars. So we can get the mass and the radius of the planet, and with that you can get the density and infer, I don't know, properties, if it's a giant planet, a gas giant planet, or a more compact and dense object like a super Earth. So today I will focus in another powerful tool that we have with the transiting planet, which is transmission spectroscopy. Since we are observing the passing of the planet in front of the star, part of the starlight will be absorbed by the planetary atmosphere. So if we can disperse that light in different wavelengths and measure the eclipse in each of these wavelengths, we will know that the depth, it will be a function of the wavelength. And that's because you have different molecules and atoms in the planetary atmosphere that will provoke a deeper transit in one wavelength or another. So we can infer the composition, the atmospheric composition of these objects. So you can imagine that in order to do that, you need really good precision. And we want in order to do these types of studies, we want to use a big telescope so we can get those precisions. In our case, we are using GTC OSIRIS instrument. Everyone here is familiar with GTC, the 10-meter class telescope in La Palma, with a field of view near 8 arc minutes. So in this talk, I will review a couple of results using the imaging mode of OSIRIS, using tunable filters, and also more recent work we have been doing with long slit spectroscopy. So, and also, besides the observations and to do the analysis of our results, I'm currently using a Bayesian approach for the light curve fitting, using modeling to get the analytical model of the transit. I use Jimenez 2006 code written by Hanu. Hanu, he's here. He also put the code recently in the web, so it's free for everyone. And to do the Monte Carlo simulation, I'm using the MC Hammer, which is a nice code written in Python to perform Monte Carlo analysis. So, okay, I'll begin with GJ1214. GJ1214b is a super Earth of 6 Earth masses. It was discovered in 2009 by Charbonneau in the survey known as M-Earth. So it was discovered orbiting around an M-dwarf and with a period of 1.5 days. So it's not in the habitable zone, but it's one of the best super Earth, transiting super Earth that we have now to study. So Roger and Seeger proposed 3 models based on the planetary density to propose 3 models to the composition of the atmosphere of GJ14b. It could be either a mini Neptune, a rock ice core with a primordial atmosphere, or it could be also a water world with a big ocean and water vapor in the atmosphere, or based on the density. All of this is based on just the radius and the mass. Based on the density, it could be a rocky planet, like rocky material with a thin secondary atmosphere. So this is where transmission spectroscopy is important, in order because each of these models can give several different scale of heights in the atmosphere. So if we can constrain or detect some atmospheric features, we can constrain better which model is the correct one. So this is one of the most studied planets, I would say. This is an example of the work of Berta and collaborators of last year, and they used the Hubble telescope to try to constrain the atmospheric composition. But as you can see in this plot, you have several different authors that have been trying to do transmission spectroscopy with this planet and trying to constrain better the models. You have Bean and Desert, Kroll, Crossfield, and so you have a really wide wavelength range of different observations. But so far, as you can see, the atmosphere of this planet doesn't show any distinct feature. It's basically flat. So this kind of supports the idea that GTC-14b, it's a super Earth with a really thick atmosphere. You might say it's a gray atmosphere that it doesn't have the light comes through in each of the wavelengths. So, but we tried to use tunable filters with GTC Osiris tunable filters. You can choose basically the wavelength of your band that you want to observe. Since one of the models says that there could be a lot of water vapor in the atmosphere of GJ1214, we choose to observe near H alpha with the hope that part of the hydrogen will be the hydrogen molecules and the water molecules could be destroyed by the flux of the star, so we can try to detect a feature in that wavelength. So with GTC Osiris, we choose three band passes, one center in the H alpha line and two near the continuum, with a really narrow filter of 0.2 nanometers. So here in the right, I show you, here it's one flat image of the tunable filters. I show you this because of the way that the instrument works. You will have rings of equal wavelengths increasing from the optical center of Osiris. So in order to have our star in H alpha, for example, we have to choose another star at the same distance from the center as a comparison. So we only were able to choose only one star given the geometry of the field to be on the same position from the center of GTC Osiris. So in that way, we are sure that the reference and GJ1214, it's on the same wavelength in each of the observations. So then we cycle the filters. We took images in one of the continuum, then H alpha, and then the next continuum. So we have 333 images and 111 for each band. So, well, for more details, this is a paper that came out this year with the results. So you can read that to know the reduction process and the analysis. But what we get, it's here, this is the light curve using the tunable filters for the three band passes, also the fit. and the residuals. As you can see, it's fairly noisy, but that's because we are looking at a very narrow wavelength range. So we have to sacrifice a little bit of the signal to noise that we can get in order to get really narrow bands. But either way, the data was a little bit noisier than we were expecting. But nonetheless, we fit the models of Jimenez to try to see, to measure the depth of the eclipse at these different wavelengths. So here's the transmission spectra of GGL1214P that we obtained using the tunable filters and comparing the work of previous works on this planet. So, well, this is the full range of current observations, and this is a zoom to the region near the H alpha line. As you can see, well, it could H alpha is the point. It's a little bit higher than the surrounding continuum, but the error bar is still big, so we cannot really say that there is an excess of H alpha in this based on these observations. And also it agrees very well with the other studies made with wider filters. So this, well, this is probably, if I'm not mistaken, one of the first study that used narrow band passes in these planets. There are other studies using tunable filters in other planets, but in a super Earth, I think this is the first one. So we cannot really say anything about this yet. Let's hope that in the future we can get more information about this. So transit spectroscopy. Now I'll talk about a little bit of the work we have been doing with the long slit spectroscopy mode. So just to show a cartoon how this works, you have these are actual images from GTC Osiris. So you have your field, you have your target and your reference. You put first light, and you end up with something like this. The spectra of each of the stars. Then you extract the spectra, so you can have the light of both stars in different wavelength regions. And once you have this, you can make, I don't know, filters, several filters, Johnson filters, and start separating the light in different wavelength ranges, so we can see if we can detect any atmospheric features. So, so our first case of study was WASP-43. This is a hot Jupiter. You can see that it has a really short period of less than 1 day, and it's a Jupiter class planet. So just to show you the precision that we can get, this is one of our data sets. It's incomplete because we have problems with the instrument here in the egress. But this is a good example to show the precisions that we can get using GTC. This is, I think, this is like outside the transit, all the points outside the transit. It's like 2 hours or 1 hour of time. And during that period, we can get precision of 0.6 millimagnitude. So under good weather conditions, GTC is really a powerful instrument. And another thing that I didn't mention is that this is the white light curve. I mean, I integrate the whole spectrum that you saw in the cartoon image, and to get this light. But anyway, with different data set that we have for WASP-43, we can get a full transit, and with that we can separate it, for example, this light curve in different filters, in the Johnson filters. What we can do with this, for example, we can study the color signature of the planet. This is something that Brandon Tingley has been working on some time. You can study the color signature of a planet when it passes in front of the star. If you take the light curve of the transit in two different filters and do the color of that, you get those horn-like structures and each of these curves depends on the inclination of the system. These are different models. But the important thing is that these horn-like structures are really typical of a planetary object transiting in front of a star. So you can use this method to try to discard some of the Kepler candidates, for example, that you cannot do really radial velocity, but you can observe it in two bands. And if you get a signal something similar to this, it's more probable that that is a planet instead of a binary, for example, a low mass binary. Also, the signal is different from a Jupiter planet or a terrestrial planet. So you can even, if you get really good precision, you can really distinguish between the different types of planets. So we try to do this for WASP-43. This is the B Johnson filter minus the Z Sloan filter, and you can see that more or less we detect the horn-like structure, the color signature of this planet. So this is one example, and then also this one is one of the most interesting cases that we're working on. This is a really weird planet from Kepler. It was discovered this year by Rappaport. You have a planetary object orbiting a K-dwarf, but the particular the characteristic, very special characteristic of this object is that more or less in each occultation, the depth of the transit varies. So here is Kepler data. This is the full range covered by Kepler. And you can see that here is where the occultations occur. This region is populated by different points with different depth. So that means that sometimes you will see the object bigger, for example here, and sometimes the object is smaller. So the current theory behind this is that it's a Mercury-sized object evaporating. So sometimes we see this object bigger because the gray cloud is bigger, and sometimes it's smaller. So we know that it should be more or less of Mercury size because Kepler doesn't detect occultation. So if it's not detected by Kepler, it should be a really, really small planet. So we use GTC to observe this transited planet, and we were lucky. We had one good transit. We were lucky that it was one of the deepest ones. So we can separate the light curves in three different not just 3, but in different filters to try to constrain the nature of the dust cloud that this planet is expelling from the surface. So this is a work led by Roy Alonso with several others from AIC. And we are preparing a publication with this. It'll go out soon, I hope. But so far, we haven't detected any difference between the colors of the so we cannot, we only can say that. It does not really help us, I guess, to constrain the size of the grain really good. And last, well, I'll talk about our recent work, very recent work with HATP 32. We have observations of this object at the end of September. This is a Jupiter object. The mass and the radius are not really well constrained because the eccentricity is not really well constrained in this planet. So you have an error in the planetary mass and planetary radius. But part of this error may have something to do with this. While we were reducing the data, if you look here really closely, this is the radial profile of one of the spectra, for example, this one. So if you look at the radial profile, you see that here has a really, really tiny bump. So we look at the acquisition images from GTC and we didn't see anything. But luckily, Enric had some William Herschel time, some observations, and he pointed the telescope, and he found that there is a little companion or contaminant next, really close to the star, about 3 arc seconds. So Lisa Nordman, one of our collaborators, first extract the PCF from HAT32, and then add all the spectra. And by adding all the spectra, you can get this really nice plot of the spectra of the contaminant or companion. So we are guessing that this is an M dwarf. We haven't really established the class, but we are pretty sure that it's an M dwarf that is contaminating a little bit the flux. So, and maybe that could also contaminate the radial velocity signal, and that provokes the problem with the eccentricity. This star may be adding a lot of jitter to the radial velocities, and that way you cannot really constrain really good the eccentricity of this system. So here's the light curve. In the top panel, you have the fluxes, the individual fluxes from the reference star and HAT-P32. This, as you can see here, there is systematic effects that we are not really sure where they come from. We have our suspicious or suspects, but we cannot really say so far with security where this comes from. It has something to do with the rotator angle, but we're not really sure. And also the problem with the trends here is that affects first one star, the reference, and then this bump, you can see it on the star with the transit. So when you do the ratio of these fluxes, you end up with this bump here, and here. So I'm still working on trying to model this, but we don't have much information yet. Here, these are just clouds that sometimes have happens and then block. But the correction it's a little bit noisier, but it's okay. It's different from this side, for example. So nonetheless, I did a fit to this light curve. I use a quadratic polynomial to model the points outside the transit, and together with a transit model. So what we can do with this is break the different spectra in different filters. For the top panel, you have the transmission spectra of HAPI-32 with bands with a width of 250 angstrom. So you can see that there is a soft trend here. And then when the sensitivity of the telescope is really bad, after 9,000, you get these weird, funny points. But the important thing is that we can have a big range of wavelength coverage using long slit spectroscopy. Also, you can see that this point and this one, it's a little bit high. It's higher than the rest, and these points correspond to the sodium and the potassium lines. Both of these lines have been detected before in transiting hot Jupiters. So we are not really sure if this is a detection or not. It could be. Here in the bottom panel, I plotted a zoom near the sodium line and with narrower filters. So these 3 points agree with the wider filter, the black dot, but you still have this and these outliers, you may say, that I haven't had the time to work on them first, but maybe this could be a detection of sodium. We still don't know. Also, I forgot to mention that if this error bar is bigger because you have the telluric lines of oxygen here, this really big line near the potassium line. So this is it's more difficult to say actually if there is a detection of potassium or not. So far, what I've been doing, actually, it's running right now. It's try to model the systematic effects of the light curve, and then after I finish this, I'll get back to this work. But this is just preliminary results, so we cannot really say anything. So, well, that's it. I'm finished, and there are a lot of things in this field that it will continue to grow, and of course, new discoveries are waiting. So that's it.
So thank you very much for the nice talk. Do you have any questions for Felipe?
In the curve for WASP 43, there was something like a bump close to the
Yeah.
What was causing that?
Yeah, this could be a systematic, I guess, because this one, in this particular set, we have a lot of systematics. So this could be a systematic effect that I'm not expecting really. So this bump, I don't think it's a spot or something like that. It's just an error in the reversion. Not the reversion, but the systematic effect I have taken out. yet. So yeah.
You had other transits of the same system.
Well, not a full one. That's the problem that we have with this particular object, that we have several data sets, but not a full one. So I couldn't really work with a full data set. It's important to have a full data set so you can take into account all the effects. Because if you are missing a part here, well, you don't have information of what happened here. So
the next plot, the plot that you just showed, that was like you symmetrize the picture. Or you made it symmetric, or how it looked like you have here both.
What do you mean?
Okay, it's orbital phase. Then.
Yeah, it's orbital phase. Yeah, I have to merge all the data set and put it in orbital phase. Yeah.
Yes, I have a question about the Kepler object. I mean, you say that you see a change in the depth of the transit, but only in the depth. You cannot see, for instance, a change in the duration of the transit.
As far as I know, no, there isn't a change in the duration. If you look at the Kepler data, it's more or less constrained. But yeah, well, a change in the duration, I don't know if that could be possible. I mean, you see, yeah.
If assuming that the planet is bigger, it looks like it's 2 or 3 times bigger.
Yeah.
Because the change is that big, but you cannot see any changes.
No, well, no, not really. I don't think so.
To reply to this, there might be marginal changes, but the problem right now has been with the Kepler data that they are taking a cadence of 30 minutes. And this is really wrapped. This is what you see, for example, the lower left are many tens of trends of these transit events where they selected only the deep ones, and the lower right are where it's the same where they selected only the shallow ones. So these are averages out of many individual events. And we don't know well if the individual events vary in duration, because up to now Kepler had only a poor time resolution. Now there have been coming out new data publicly very recently ones with a 1 minute time resolution.
Yeah.
And in these, one doesn't see it very well either, because they're much noisier now in turn, because basically the RMS has increased due to the shorter exposure time. There's probably the shallow events are possibly shorter, but it might be only a perception due to the disappearing more easily in the noise, the signal. So the main thing is a different depth signal. What has also shown up in the short cadence ones in Kepler now is that the deepest ones are actually 2% deep nearly.
Okay.
Which has just been smoothed out in the older
Okay.
data.
Oh, I haven't taken a look to the short cadence data, but
so the one we observed with GTC was actually an intermediate depth event.
Yeah, well.
Any more questions? I have one question. You said you have the systematics, some suspects. What are the suspects?
It could be something to do with the flat field, that the flat field changes according to different positions of the telescope. But since we are doing really high precision photometry, you cannot really see it in ordinary data. But with this, you can notice. So there is a weak correlation with the rotation angle of the slit, but that's the only information that I have. So for now, I'm just modeling this, basically taking a model by eye. By eye. So it's not a correlation based on the rotation angle or something like that. I just put a high degree polynomial and with the transit basically, and see what happens.
Okay. Thank you very much, Felipe, and yeah, have a good.